So let's examine the proteins and the enzymes that are going to be functioning at that replication bubble. Okay. You have, well, here if you look in this figure, there are many proteins and enzymes that are working in concert. Okay, this is just a small picture of some of the proteins and enzymes there, just a sampling. There are going to be many more, and we're not going to worry about those. We're just going to focus on these for right now. You have an enzyme known as helicase. Helicase, think of this as the zipper. It is unzipping the double helix, physically pulling apart the two strands. Now, while the double helix itself is somewhat stable, you wrap the double helix around proteins, it becomes very stable. Individual strands of DNA can be bent and broken relatively easily, unless you have something there to protect them. And that's where the single-stranded binding proteins come in. Okay, their job, these proteins bind to that single strand of DNA to support it, to keep it from being bented or twisted around too much and breaking. You've probably seen it when you have a string or even say like a phone cord, that's in that helical pattern. When you stretch it and you bend it, you keep playing with it too often, whether it's the string, the phone cord, a knot is going to form. Well, think about it. If you're unwinding this double helix and you're unwinding it at hundreds of nucleotides per minute, this is actually quite fast. You're going to get lots of stresses, lots of kinks, and knots can be formed unless you have a way of releasing the tension. And that's where the enzyme Topo Isomerase comes into play. What Topo Isomerase does is it's situated, dozens, if not hundreds of nucleotides ahead of the replication fork, and it will cut, as you see here. It will cut one of the strands, allowing the double helix to release some of the contortional stress. Allows it to release some of the stress, and then topoisomerase will seal it back up. So literally, where it cuts, it allows it to spin, releasing stress, releasing some of the pressure, and then it seals it back up, and then moves down the double helix somewhere else. Does it again. And then finally, we have the enzyme known as primase. Primase lays down RNA primers. Think of the RNA primer as a starting block. For DNA replication to be initiated, to start, it has to have something to build on. Hence, an RNA primer. RNA primers, anytime RNA gets inserted in DNA, repair machinery immediately comes and pulls it out and replaces it with DNA. So this RNA primer is just a place to start, and then repair machinery will move that and replace it with DNA later. So, as I said, the replication fork is going to have many proteins and enzymes, but some of them that we are going to focus on: helicases, single-stranded binding proteins, and topoisomerases. Because the big player is DNA polymerase. Ends in A, so it's an enzyme. What prefaces A tells you what it does. DNA polymer making enzyme. Specifically, DNA dependent DNA polymerase. DNA dependent reads DNA polymerase to make DNA. One of the weird things about DNA polymerase, whether you're talking prokaryote, eukaryote, it needs something to build on. It cannot just start laying down anywhere the new strand of DNA. Hence, the RNA primer, put into place by primase. This gives a building block, a building start point for DNA polymerase to come and start adding to.